Hey boys and girls, so today we're going over Unit 8, Lesson 1. Make sure you have your name written at the top, and then we can jump on in here. All right, so Lesson 1 is about what are similarity transformations. So this is going to take everything you learned in Unit 7, and we're going to really start applying it here in Unit 8. Let's look at the do now. It says, carefully examine the given figures and decide if there's a sequence of a dilation and a rigid motion that takes the small figure to the large figure. And then we have to explain. So I'm just going to go through and highlight out what's important. Sequence is a key vocabulary word. So is dilation, rigid motion. All right. And then I'm just going to underline the question at the end here where it says, what's going to take the small figure to the large figure? All right. And then we have to explain that at the end. All right. I know that the keyword sequence means more than one. So I'm just going to write that down. All right, I know that a dilation can change the size of something, and I know that a rigid motion does not change the size, okay? It preserves everything, side length and angle measure. This guy only preserves angle measure, all right? So here we go. If I want to explain if these could map, right, the small guy onto the big guy using a dilation and a rigid motion, what would you say? Would you say, yes, that's true, or would you say, no, I don't think that is true? Well, as I'm looking here, it looks like everything about the Mickey on the left looks exactly the same, only it's all been enlarged to get the Mickey here on the right. So I would say that yes, there is a dilation. That dilation would be greater than 1. That's going to map my small Mickey onto my large Mickey, because since he's getting bigger, I know my scale factor would have to be greater than 1, like 2, 3, 4.5, something like that. Okay, so the dilation part checks. What about a rigid motion? Yeah, I would say that after I dilate, I would follow that up. So that's going to be followed by a translation. Does anybody remember the definition of translation? Absolutely. It just moves something. It slides it over. So I'm going to say after I translate that little Mickey to the right, it will map right on top of that large Mickey. And that's exactly what I wanted to happen. All right, cool. Now let's look at the stick figures here. This one's a little bit more tricky because as I'm looking at the small stick figure and the big stick figure, be really careful even with the way I'm saying it. I don't think everything about this guy is small and everything about this guy is big. It looks like only the head dilated. It looks as if the bodies are exactly the same. So would you say that there's a dilation that's going to map the guy on the left to the guy on the right? I would say no, absolutely not. In a dilation, everything is going to change size and only the head change size. So I'm going to say that no, the bodies are already the same size. So only the head needs to be dilated. All right, so that one was a little bit more tricky. Every year, a lot of us usually say, yes, there is a dilation, but be really careful. A dilation changes everything in the diagram, okay? Not just one piece of it. Underneath, it says, using a compass and a straight edge, we want to describe the sequence of the similarity transformation shown below. Again, I'm going to grab my highlighter here and go over what's important. So I have to describe the sequence of similarity transformations shown below. We already said that sequence means more than one. I'm just going to box that out and write it one more time. More than one. All right, and I know that more than one thing should be happening here because I have my pre-image, ABC, my prime, A prime, B prime, C prime, and my double prime. All right, so it looks like I have to do one transformation followed by another transformation. All right, here we go. As I look how I would map my pre-image onto my image, immediately I'm noticing that the size has changed, and I know that represents a dilation. So on the side, I'm just going to start off by saying that the first similarity transformation would be a dilation. Now, when I describe or I talk about a dilation, I have to include two important things. I have to say the scale factor and the center of dilation. So I'm going to say it's a dilation of scale factor, and I'm just going to put a blank for now because I don't know what it is yet. And I'm also going to write centered at, and then again, I'm going to put another blank because I don't really know where the center is just yet. All right, I'm just setting myself up here so I know I don't leave anything out. Well, if you remember back to Unit 7, when you don't know where the center of dilation is, you just connect corresponding vertices, and where they cross would be the center. So I'm going to connect A and A prime because I know that those correspond. So I'm going to use my straight edge here, use my ruler. I'm going to draw a nice big line here. Really, I'm making a line segment. All right, and then I'm going to do it again. I'll do C and C prime this time. It doesn't really matter. So here we go. I'm lining it up perfectly. All right. And as I look back here, I can see that they cross right down here. I'm going to label that O. Because if I say it's centered at, I have to say it's centered at either a point on the coordinate plane, but I don't have a graph here. So I'd have to use some type of letter. I'm going to use O because O isn't being used in this diagram already. Now I have to figure out what the scale factor is, and I'm going to use my compass to do that. So I'm going to take that clear section, the bullseye, the pointer, whatever your teacher calls it, and I'm going to line it up nicely on my center of dilation, which is point O. All right, then I'm going to take my finger and hold it in place. Now I'm going to move my slider. So when I look through either the inside or the outside hole, it doesn't matter. Right now I'm going to use the inside hole. I can see A prime, that image point. All right. Now I'm going to take my entire compass and I'm just going to slide it on up. Now I want my pointer on A prime. And when I look through again, that inside hole, do you notice now I'm seeing A, my pre-image? Well, this is telling me that the length of O to A, the length of this segment is double the length of O to A prime. I know that my scale factor has to be less than 1 because my triangle is getting smaller. So instead of doubling the length, it looks like I am now halving the length. So the scale factor would be 1/2. So that was our first transformation. Now I have to think, well, how do I get from the prime to the double prime? Well, I don't know about you, but I can tell that this is not going to be a translation because if I slide the prime up, it won't map right onto the double. And it doesn't look like it's going to be a rotation because if I check the orientation, A double to B double, A prime to B prime, I can see that the orientation is reversed. And the only time that happens is in a reflection. All right. So I can tell that these triangles are equal in size and shape. So I know that the side length and angle measure is preserved. That makes it a rigid motion that's taking place. And the rigid motion would be a reflection. All right. So that's going to be my next answer here, a reflection. But anytime we reflect, we always reflect over a line segment. And right now I don't see one. I have to create it. So here we go. I'm going to create a line segment from B double to B triple prime here. And then I'm going to make my football. I'm going to make a perpendicular bisector. That's how you create your line of reflection. So I'm going to line up my pointer or my bullseye, clear section, whatever you call it, on B triple. I'm going to move my slider so it's more than halfway. And then I'm going to swing and get that nice half circle. Then I'm just going to turn it around and do it again. All right, here I go. And then I can see that where my arcs are crossing up top and below, that's where I want to move my ruler so I can draw that line of reflection here. Okay, I know that lines go on forever, so I'm going to add arrows to the top and the bottom. And now I have to label that line so I can say on the side, I'm reflecting over line what? So again, in this diagram, I don't see the letter L. I'm just going to use L for line. So I'm going to say I'm reflecting over line L. All right, cool. If you look underneath, we have some more notes. So this is huge for this unit. This symbol represents the symbol for similarity. Please highlight this with me if you can. All right, if not, make sure you box it or star it. Okay, it's really important. So there's two symbols now that you've learned as far as congruency and similarity. All right, we have the congruent symbol. That means two things are equal. They're exactly the same. And now we have the similarity symbol, which is a little bit different. I wouldn't say two things are identically the same. I would use these notes that I've already filled in at the bottom here. So if two things are similar, that means that the side length won't be equal because that would be congruent. The side length is in proportion. Okay, that's what makes the figure similar. But angle measure is still preserved. Okay, so whether it's a rigid motion, proving congruency, or its similarity, angle measure is preserved, but the side length is what's changing here. Side length is in proportion. All right, and if I look at these examples down below, both smiley faces look exactly the same. Again, the only thing that's changing is the side length. These two smileys would be in proportion with each other. Characteristics. This is how we could shorthand it. Okay, you wouldn't write this on a test or a quiz, but when you think similarity, you should be thinking same shape, different size. All right, so this would not be an example of similarity because they have the same shape, kind of. Like this is a circle and this is an oval, right? So they really don't even have the same shape. And yes, they're different sizes, but again, it doesn't follow both of these together. Okay, so this would be an example of same shape, different size. This would not be. Okay, I'm also writing it can be different size because you'll learn about that more towards like the middle and end of this unit. Okay, so we'll talk about this later on. As we look at the notes towards the bottom here, let me just slide this up a little bit more. It says to be similar means to have the same shape. I'm going to highlight that out here. If I want to be similar, that means I have to have the same shape. If I want to be congruent, that means I have to have the same size and the same shape. So underneath, when it says congruent figures are also what figures, I'm going to say congruent figures are also similar figures. Because if I'm similar, I have the same shape. And if I'm congruent, I also have the same shape. All right, but I can't say them in reverse because if I'm congruent, that means I really have the same size and the same shape. All right, so be careful. Let's move on to the next page. All right, so I'm going to go over some of these with you just to start, and then I'm going to have you finish this section on your own. So it says, for each of the following, state the transformation taking place. All right, well, I know that there's a few different transformations we've learned. Technically, there's 4 of them. Dilation, reflection, rotation, translation, right? So I have to figure out what transformation is taking place, and then I have to state whether those figures are similar or not. All right, and I should be thinking of the definition we just went over on the first page for similarity. Here we go. It looks like I have 2 cell phones here. They look exactly the same, except one is up top in the left, this one's down below on the right. What moves or slides things out of the way? A translation. Excellent. And now part 2, it says, is this going to be a similarity transformation? Well, we just learned on the front page that congruent figures are also similar figures. So yeah, they are going to be similar. I'm going to write yes. And I know that they're also going to be similar and not just congruent because angle measure is preserved. Add that on with me. Angle measure is preserved. All right. So one more time, if I just flip back to the front at the bottom here, I know that congruent figures are also similar figures. Congruent would be a translation, but it's also similar. So the answer was yes. And then why? Because the definition of similarity says that angle measure is preserved. Angle measure is preserved in both similar and congruent figures. That's what's making it similar. All right. If I flip back here, now I'm going to have you guys try those next 3 on your own. So at this point, pause the video, try those out, and then check back for. All right, here were the answers. So I can see here that this cell phone just turned. That would be a rotation. This changed size, that's a dilation. And you can see that the birds are reflected here. It looks like a mirror image. So again, that would have been a reflection. And then are these all similarity transformations? Yes. Of course, a dilation is a similarity transformation because if 2 shapes are similar, it would have to be because they have the same size and shape. That's what a dilation is. But again, a rotation and a reflection also preserve angle measure, just like a translation does. So technically it's making all of these similarity transformations. These are similar because they have the same size and shape. Again, similar, similar, similar at the top. All right, let's look at example 1 down below. I'm just going to slide this paper up a bit. Here we go. So it says, given triangle ABC with those vertices of A 2, -7, B 2, -2, -1, and C 3, -4. Identify the sequence of similarity transformations. Okay, again, I'm going to highlight what's important here. Sequence we went over on the first page. We know that means more than one. And similarity transformations, well, we just learned from up top, there's 4 similarity transformations we can pick from. It could be any of these guys. All right, so just be aware of that. So let's move back up here so we can get started. So I'm just gonna look for my pre-image, just triangle ABC. Again, they gave me what those coordinates are, so I'm just gonna go ahead and highlight that out. So here is triangle ABC. Again, I'm just a visual learner. This helps me just see what's happening here. And now I'm gonna look for my prime triangle, the first transformation that takes place. And here it is. I have B prime, C prime, and I don't see A prime, but I can see that they connect to A. So I'm just gonna keep that alone for right now. All right, now I gotta ask myself, how am I going to map my orange onto my pink? Well, if I look here, I can see that B is on the left, B prime is on the right. C is on the right, B prime is on the left, and A didn't move. So I'm right now thinking it's going to be a reflection, just because if I draw a line right down the middle here, I can see that from this line, instead of going 4 to the left for B, it's 4 to the right for B prime. If I extend that line further down, instead of going 1 to the right for C, it's 1 to the left for C prime. And that's the definition of a reflection. All right, those points are equidistant from the line of reflection. So I'm going to draw this line in, and this would be my first similarity transformation. It would be a reflection. So on the side, I'm just going to number that. Here's my first transformation. It's a reflection. But just like we talked about on the first page, I'm reflecting over lines. Well, what's the equation of that line? Well, I'm hitting the number 2. 2 is on the x-axis, so this would be the equation x equals 2. That's the line. So I'm reflecting over the line, x equals 2. All right, cool, moving on. It's number 2. Let me grab a different color here. All right, so now I have to look, how am I going to map my prime onto my double prime? Well, I can see that my double prime is down here. So again, I'm just going to highlight it out so it becomes a little bit more clear as to what's happening. All right, let's check it out. Well, here's C prime, here's C double prime. Here's B prime, here's B double prime. Well, what similarity transformation just turns, or again, rotates a figure? That would be, yep, a rotation. Now let's get in rotation. So sorry, guys. Okay, so when I talk about rotations, I should be thinking about what's my center of rotation and where am I rotating until? How far should I go? All right, so I'm gonna look here. Do you notice to get from my pink to my blue that the center of rotation would be A? I don't have an A prime, an A double prime. All right, so A is my center of rotation. I'm taking the pink and I'm just dropping it down. I'm just turning it over here to get my double prime. All right, so my center of rotation is A. So I'm gonna say it's a rotation about point A. And I'm gonna say that I'm gonna continue rotating until, now I just have to pick one pair of corresponding angles and then I'm done. So I'm gonna say B prime maps onto B double prime. And again, you have to use that angle symbol. So it's until angle B prime maps onto, it's got to rotate right on top of angle B double prime. All right, and I'm done with number 2. Now I got to just look for that triple prime and I can call it a day. So here we go. Let me grab the yellow for this. So here is my double prime, the blue. Now I'm looking for my triple prime, which I'm going to highlight out now in yellow. All right. I can see that the size is changing, and the only thing that changes size would be a dilation. So I'm going to say step 3 would be a dilation. And anytime we talk about dilations, I have to say what my center of dilation is and my scale factor. So I'm going to say this is a dilation of scale factor blank, just because I don't know what it is yet, but I will find it. And then I'm going to say that it is centered at blank, because again, I don't know what the center is yet, but I will figure it out. All right, let's do the center of dilation first, because that's pretty simple. If you think back to the first page, we didn't know what the center of dilation is, so we just connect corresponding points to find it. I'm going to connect with my ruler here, A to A triple, because those correspond. And then I'm going to connect B double to B triple, because those correspond. And if you want to go one more, I could connect C double to C triple, but you don't have to. All right, just keep that in mind. As soon as they cross, you have found that center. I can see that all of these lines are crossing at the point 6, -1. So I'm just going to write that on the side here. 6, whoop, -1. All right, so that's going to be my center of dilation. It's going to be the point 6, -1. Okay, I'm going to put it inside parentheses because it's a coordinate, x, y. Now I got to figure out what the scale factor is. So I'm going to use the same method I used on the first page. I'm going to put my pointer, that clear section, the bullseye, whatever you call it, on the center of dilation. I want to line it up nicely as best I can, and then I'm going to hold it in place. I'm going to move my slider down, so when I look through one of those holes, I can see B double prime. I'm sorry, B triple prime up top, the little guy. All right, I'm using the inside hole right now. All right, and here's my center of dilation. I'm going to take my entire compass and I'm just going to whoop, slide it down. So now my center is on B triple, and my pointer, when I look through, I can see it's on B double. So this is telling me that this segment from my center to B double, this is twice the length as B triple prime here, okay? So instead of me wanting double the length, I really want to go in reverse. I actually want half the length, because this triangle is getting smaller. That means my scale factor is less than 1. So again, instead of doubling, I am halving. So what's the scale factor? It is 1/2. It's actually the same scale factor as the question on the first page. All right, boys and girls, here we go. Example 2. It says, given triangle ABC as shown on the diagram of the coordinate plane, part A. Perform a translation to triangle ABC so that vertex A maps to the origin. Then we have to state the coordinates of triangle A prime, B prime, C prime. That would be the image, that new triangle we're going to create. Okay, as I'm reading this, I see the keyword translation. I know a translation means to move or to slide something out of the way. And it looks like I'm going to move, or I'm going to translate vertex A so that it maps to the origin. So here is vertex A. I want to translate it so it maps right up here to the origin, which is 0, 0. All right, you guys know how to do this part, so I'm going to let you complete part A on your own. So at this point, pause the video and then check back when you're done. All right, here we go. Part A is complete. We translated A up to the origin to get A prime. And by doing that, I really had to translate or move each coordinate left 6 and up 4 units. All right, so I did the same thing for B. Left 6 up 4 to get B prime, to the left 6 up 4 to get C prime. Again, we were creating a triangle, triangle A prime, B prime, C prime, so don't forget to go back and connect all those vertices to get that triangle done. All right, next, part B. It says, next we want to dilate the image, A prime, B prime, C prime. I'm going to highlight that. So we want to dilate. That means we want to change the size, typically, of A prime, B prime, C prime from the origin using a scale factor of 1. So anytime we dilate, we need to know where the center of dilation is. It looks like the center is the origin. And we also need to know the scale factor. Scale factor is 1. Now this is important because if you think back long ago, we had learned this, that when you are dilating from the origin, you can use that trick where you take the scale factor and you just multiply it to all of the coordinates. But I know that anything times 1 is itself. So are any of these going to change? Absolutely not. So explain what happened. Nothing. Nothing is going to happen here. All of those coordinates are going to stay the same. All right. So this triangle that I have up top isn't just going to be my prime triangle. It's also going to be my double prime triangle as well. So this isn't just going to be A prime, this point. It's also a double prime. Up top isn't just B prime, it's also B double prime. And at the bottom, that's not just C prime, it is also C double prime. All right, moving on to part C. It says now finally we want to translate the image A double, B double, C double prime so that vertex B double prime maps to 8, -1. Again, I'm going to go back and highlight what's important here. Translate is a key vocabulary word. That tells me I want to move it out of the way. I want to slide it. I'm going to be sliding or moving A double, B double, C double prime so that vertex B double prime maps to, that means I want it to move right on top of 8, -1. So now I got to ask myself, well, if I want to move or if I want to slide B double prime, which is up here, right? Because we know that this is also B double. If I want to move this point so it maps onto 8, -1, well, 8, -1 is down here. So this is where B triple prime is going to be. But now I have to ask myself, how do I get from here to here? It's very similar to part A. Well, if I count the boxes, it looks like if I go to the right 7 units and then I move down 4 units, that's how I would map B double onto B triple. And then I have to just follow that same pattern for the next 2. So again, please pause the video and get that section done. All right, here we go. That would have been our answer for part C. Again, I am translating triangle, A double, B double, C double prime. So again, if I'm translating a triangle, after I do that, I end up with another triangle. So please don't forget to go back and connect all of those vertices with your ruler. All right, looks like we are done with example 2, and now we are going to make our way down to example 3. All right. So if we look at example 3 here, I already started graphing the first sentence just to save a little time here. It says given O, which is 8, -3. I can see O is right here, okay? And it says I also have quadrilateral B, C, D, E with all of these coordinates. All right, and again, I already graphed those. It says state the coordinates of the vertices of the image of B, C, D, E under the following similarity transformation. So here we go. I have to state the coordinates. I can't forget to do that when I'm done, of what the image of B, C, D, E will be. I'm changing this to get something new. And I'm going to do that by following the similarity transformation down here, okay? So as I read this, it says first we want to dilate that quadrilateral centered at point O. All right, so I'm going to highlight that out because when you dilate, we need to know the center and the scale factor. So it's centered at point O, which is -8,3, and it has a scale factor of 3. So that's the 2 important pieces of information that I needed. It says then I'm going to reflect over the x-axis. So I'm going to hold off on that section quickly. I'm going to do one transformation at a time. So first I want to dilate from center O with a scale factor of 3. If you guys remember back, I believe it was unit 7, right? It was right before this unit. We had learned how to dilate when the center is not the origin, okay? Since my center is O, I have to just use slope. Really, I'm just counting the boxes to get from O to any of these points, and then I have to do it as many times as the scale factor says. For example, if I want to get from O to B, just because I plotted B first, to get from O to B, I have to go to the right, 1, 2, 3, and down 2, 1, 2. So if I go to the right 3 and down 2, that's a scale factor of 1. If I go to the right 3, 1, 2, 3, down 2, that's a scale factor of 2. And if I do it one more time, to the right 3, down 2, that would have been my scale factor of 3. So this is where my new coordinate for B would have been moved to after I dilate with a scale factor of 3 from that center. All right, we're going to continue doing that on E, C, and D. So let's count it again from O to E. It's to the right, 1, 2, 3, 4, down 1. That's a scale factor of 1. 1, 2, 3, 4, down 1 is a scale factor of 2. 1, 2, 3, 4, down 1, that's a scale factor of 3. This is where my new coordinate for E would have been. All right, and then we just continue that process. So we got 1, 2, 1, 2, 3, 4 for C. 1, 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4. Down here is where my new coordinate for C would have been. And then one more for D. I just want to double check. Good. You guys can see this on the camera. 1, 2, 3, 4. 1, 2, 3, 4. All right. Again, that's a scale factor of 1. 1, 2, 3, 4. 1, 2, 3, 4. Scale factor of 2. 1, 2, 3, 4. 1, 2, 3, 4. That's my scale factor of 3 because I have counted again that slope 3 times. Scale factor of 3. Now I'm going to go back and with my ruler or with my straight edge here, I'm going to reform quadrilateral BCDE. You guys should be doing this as well. All right, at any time if I'm going a little too quick, please feel free to pause the video, all right, so you can catch up. All right, so well, I should really say the first part is done now. First we dilated. Here is the triangle I get after I dilate. All right, and again, I'm sorry, it's actually not a triangle, it's a quadrilateral. It's just a 4-sided shape. All right, so now if I go back for the next part, it says now I want to reflect that thing over the x-axis. All right, so again, we love to highlight in this class. I'm going to highlight out the x-axis because this is where I want to jump. I want to go right over, I want to reflect right over that line segment. All right, so here we go. Let me just grab a different color here. Let me do the purple now, or actually let me do the pink. All right, since point E, this new guy is on my line of reflection, he's not going to move. So this is again where my E prime would have been, okay? Notice how I didn't label any of these with a prime. It's because I'm moving my triangle. I'm really moving it. I know I'm moving it 2 times, but this is really one big transformation, okay? So I'm originally tiny, right? C, B, E, D, this quadrilateral on the side. After I dilate it and reflect it, that's my final shape. So this is where I want to end up. So I'm going to say this is E prime. All right, from my line of reflection, instead of going down 3 units, I want to go up 3 units. 1, 2, 3. Here I go. And this is where B prime would have been. All right, same thing for C. Instead of going 9 down, I want to go 9 up. That would have been C prime. And then again, instead of going 9 down, I want to go 9 up. And this is where D prime would have been. I need to go back and connect all of my vertices with my straight edge, with my ruler here. I want to make sure it looks nice and straight. All right, boom, boom, boom. Okay. And then again, after we have reflected, this is where that final triangle would have been. All right. You guys know us, we love to highlight, so I'm just gonna highlight out this is where I would have ended up at the end here, okay? But if you look back at the question, it says I have to state the coordinates of the image, of what the image of B, C, D, E would have been. So on the side, I have to make sure I list those out. So I have B prime, C prime, D prime, and E prime. So I'm just going to go and see what those coordinates are. So B prime here is going to be +1 and then up 1, 2, 3. So this has the coordinates of 1, 3. C prime is -2, +9. D prime is +4, +9. And then E prime stayed in the same spot. He didn't really move, so that's 4, 0. All right, and then at the bottom it says, is quadrilateral B, C, D, E, similar to quadrilateral B prime, C prime, D prime, E prime. So where I started and where I finally ended up, are these guys going to be considered similar? And the answer would be yes. So let's fill that in. Yes. And it's because corresponding sides are in proportion and angle measure is preserved. All right, I'm going to explain this in a minute. I know that a dilation preserves angle measure, and I know that a reflection is a rigid motion, so that keeps all of the side lengths the same, but a dilation doesn't do that. So it doesn't keep the side lengths the same, it keeps the side lengths in proportion, all right? Oops, so sorry, you guys can't see what I'm doing down here. There it is, all right? So again, this is how I know that the answer is yes. If you guys look back on page 1 of the notes, I'm just copying this from the definition of similarity on the front. All right, you guys did a great job. Make sure when you flip, whoop, where am I? Oh man, I don't have it. So sorry. After you flip this page, that would have been your homework page, so make sure you guys are getting that done and turning all of your work in on